Olá pessoal, tudo bem com vocês? Bem-vindo a mais um vídeo da nossa série de apresentação dos professores do curso de Física. Hoje eu trago aqui o professor Roman Pasechnik. O professor Roman é o nosso professor aqui do curso. Ele também é professor visitante, né? Ele não é permanente, mas é um exemplo da nossa colaboração internacional com os nossos professores. Eu vou pedir um pouco para o professor Roman se apresentar e ele vai fazer uma apresentação para a gente. Professor Roman, welcome to our series of videos. Thank you very much for participating on this and willing to participate and making a presentation and all. Professor Roman, I'm going to ask you what I'm asking to everyone. Who are you at the Federal University of Santa Catarina?
Yes, thank you so much for giving me the opportunity to make a presentation for students. I am a visiting professor at UFSC, working together with Emmanuel Bolivier group, collaborating for a number of years, and so far it's been my second year finished already at UFSC. I hope to continue for a longer time. Let's see how that happens. I have been teaching a few courses at the graduate program. I think one of them was cosmology, astroparticle physics, quantum field theory, classical mechanics, so there's fundamental advanced courses, and one more which I don't know the name in English. Some additional topics of research and education. Yes, so I'm permanent professor at Lund University in Sweden, where I am at the moment, hiding from coronavirus. But technically I should be soon in Florianopolis, so in case somebody is interested talking to me about research, I'm very happy to do so. I'm very open. I'm collaborating with many students throughout the world, giving alone in Florianopolis with a few in Emmanuel's group, but also in several different countries, also in Brazil, but in other institutions. So my research areas are in understanding the fundamental structure of particles and interactions at very different energy scales, starting from scales of standard model particle physics and higher. The new physics energy scale is one way of looking for new physics, so-called new physics, through particle interactions. And we study those interactions at particle colliders, such as Large Hadron Collider, and there are several more colliders that are being planned right now in the world. I'm also interested in understanding lower energy physics, in quantum chromodynamics in particular, like properties of the quark-gluon plasma, phenomena associated with hadron interactions, hadronization, formation of bound states from heavy quarks, light quarks, heavy quarks as well. The structure of hadron structure, the underlying skeleton of the proton and other hadrons, trying to understand the distributions of constituents inside the proton, which translates into multidimensional picture of the proton, and also the QCD in infrared limit at large distances associated with dynamics of confinement of color. Besides this, I would say these are two of my biggest interests. Physics within beyond the standard model is one, and QCD phenomenology is another one. The third biggest component of my research is cosmological connections of particle physics. All what I said in the first two areas applied for cosmological environment. In general, there are issues like dark matter, there are issues with production of baryon asymmetry in the universe. There are problems associated with origin of dark energy and the formation of the ground state of the universe in the course of the phase transitions. Phase transition dynamics is part of this third big topic. So I would say these are three biggest topics of my research. Yeah, so you may ask me questions if there's something specific I should mention.
Thank you very much. I think that now we can go for your nice presentation that you have prepared for us, and then we can see the topics that you are talking about.
Yeah, to make this kind of beginning of this discussion a little more exciting for students, here you can see the quote at the bottom of the front page by Stephen Hawking. I'm pretty sure students heard about Stephen Hawking, the most famous expert in gravity and cosmology in many things. So one day he has said, "My goal is simple. It is a complete understanding of the universe, why it is as it is, and why it exists as it is." So if you want to ask me what is my goal, I mean, that's probably the closest quote that I can make from other, well-known people like Stephen Hawking. Of course, that's not my favorite quote. There's several others. But that's the one which I kind of put forward here, because that represents kind of my vision about what has to be done for research in the fundamental science, and what I'm trying to do for like 2 decades almost in my research career. So to talk about what are the different branches of science that myself in particular interested in, and where the basic problems are that we are trying to address, is best represented in the scheme. I just made this scheme that shows the different length scales, temperature scales, and energy scales in fundamental physics. From the microscopic to macroscopic world, and just somehow the universal coverage of the scales is what I think is interesting, is to understand what would be the theory of everything, in a sense of covering different areas of research in different energy scales. So clearly the largest energy scale in nature that we know about is the scale for quantum gravity, which is around 10 to the 30 electron volt, which is probably the largest scale humanity could ever think about any kind of physics there, because it is even believed that the usual space and time cease to exist at that scale. But actually that's probably the energy scale and the associated so-called Planck length scale, which is 10 to the minus 37 meters, is where everything has started from. And the whole universe has popped out as a quantum fluctuation at that scale, and somehow the whole space-time became emergent and expanded, turning into our universe. And the whole matter and the whole geometry has been originating from the totally unknown dynamics at that scale, and that envelopes gravity as part of this dynamics, but also all the particle physics as we know has to emerge from that. So how exactly that has happened, we don't know, but there is a huge research activity, and thousands of researchers around the world thinking about that all the time. But then something that we can actually probe in laboratory measurements is what is called standard model of particle physics. That lies around the energy scales somewhere around 10 to the 15 electron volts, and the length scales considerably around that little line that I just drawn, and a bit higher. So that's basically the best microscopes of nature. Why microscopes? Because we are talking about probing the dynamics of ultra small separations, the distances, and the ultra large energy scales associated with those distances. That's basically the particle colliders, right? And the highest energy particle collider today is at CERN, called Large Hadron Collider, which collides protons at energies something around 13, 14, is projected to go up to 14 tera-electron volts. That's the largest energy achieved in the laboratory so far, and that's where a lot of things happening. For example, when you collide protons with those energies, you start to probe structure of the proton itself, like microscopic distances inside the proton, where the new degrees of freedom that the particles that do not exist at large distances and time scales, called quarks and gluons, start to emerge. They move practically independently from each other. There's practically zero interaction of them at small distances, but very, very strong interactions emerge when they move apart from each other. So this is the peculiarity of the so-called strong interactions, which is part of the standard model, and quarks and gluons, which are carriers of the strong interaction between the quarks. Those are a natural part of the standard model framework. But then there are additional sectors. There's the leptonic sector. Those are particles which are relatively light, like electron, a muon, a partner of electron, and also the tau. These are the charged lepton sectors. They interact electromagnetically and weakly, and there's also neutrino sector, which only weakly interact in sectors. So the weak interactions is also part of the standard model. So we have weak interactions, we have electromagnetic interactions. Well, actually, proto-electromagnetic, the one which happens above energy scale of around 1 giga-electron volts, but then below 100 giga-electron volts, but then below that scale, the electroweak symmetry is broken, and we only get electromagnetic interactions surviving. The only gauge boson in the standard model that survives is the photon, which can propagate at cosmological distances. But the vector bosons acquire very large mass and become unstable. So this electroweak sector, which is part of the standard model, and strong interacting sector. So these are the two such sectors that are neatly united within the standard model framework. So we know about the standard model and all these interactions, like weak electromagnetic and strong interactions, about these three interactions. We know practically everything already. Measurements made in 1,000 different processes at very different energies of particle collisions. At least whenever we can apply perturbation theory, we already know a lot. Still, people look for tiny effects of the so-called new physics, phenomena that are not part of the standard model framework, like looking for additional fermion states and also additional scalar states. Recently, the last piece that was observed was the Higgs boson state, which through interactions with fermions and heavy gauge bosons gives them masses. But only one such state has been found, and there are arguments from the theoretical and cosmological studies that we do have to have at least one more or a few more such states, and that's what part of the LHC program is, to look for those states. But also there are additional possibilities for additional vector-like states, like leptons and quarks at higher mass ranges. So those are not just additional generations of the fermions, but they are just heavy vector-like states that people look besides the scalars, also additional gauge bosons as part of this many new physics frameworks is to expect that there are additional gauge boson states and so on. The reason why we look for new physics beyond the standard model, even though the standard model is well tested and works amazingly well at all these thousands of different scattering processes, is that there are such issues as neutrino problem. We don't know how neutrino exactly gets its mass and how it mixes, and we also do not know what the dark matter is, which is like almost 30% of the mass of the whole universe is dark, and it's not part of the standard model. So we do have to offer some ways to explain both neutrino problem and the dark matter problem, but also to explain on the same footing why the standard model comes so successful. Actually, people are completely puzzled by now. Why standard model framework, which was just one of hundreds of different ways how the particles and interactions can arrange themselves. Only one of them actually worked so well. And there are many questions about this framework itself, like why we have three families of both leptons and quarks, why we have the energy scale very specific and very, very far away from the Planck scale. There are so many questions here that remain unanswered. Many parameters in the standard model were just measured but not predicted from the first principles. And if we cannot calculate them from the first principles, then the question is from which fundamental dynamics they originate from. Can we have a unification of those couplings at a high scale? So that's one of the basic questions about the origin of the standard model structure from some more fundamental force, a more unified force that unifies couplings and interactions and all the states together. So there are many ways how theoretically one can build such an extension of the standard model where one or a few such problems can be solved. There are specifically cosmological problems that I could mention. For example, the baryon asymmetries needs to be generated by some mechanism. That mechanism actually requires a lot of additional degrees of freedom or a lot of additional dynamics that is not part of the standard model. So it's another example of that. Also, the other 70% of the mass of the standard model is also dark, but it's kind of uniformly dark, not like structurally dark, like you have some clumps that are dark inhomogeneities, but it's totally homogeneous medium gives 70% mass of the whole universe called dark energy. And that's also not in any way explained by the standard model. So there are a number of such issues that need to be explained, and that's what my research in kind of many different ways connecting to these problems, right?
What's your take on the monopole, magnetic monopole? Because I mean, there is some. You can predict some existence of the magnetic monopole or dark monopoles on this scale of energy.
Yeah, there is such a thing as called magnetic monopole problem that despite of some theories predict them naturally, we don't see them in experiment. The natural question, why? Either theories are wrong, and that's a good thing about research, that we can always prove theories wrong. But that can only be proved by a measurement. So either theories are wrong because measurement does not give that to you, or just measurements are not sensitive enough, and maybe this magnetic monopoles are very diluted in the universe. Maybe in the visible part of the universe there is only one monopole or less than one, and that means that they are so far away that there is no way to measure them, to detect them, right? So that's one of the ways, for example, cosmic inflation tries to address this question. It says that, well, initially you had a lot of magnetic monopoles when the universe was of the size, microscopic size of a quantum fluctuation. But when it's inflated to the sizes like we have today, which is hundreds of gigaparsec or something, then through inflationary mechanisms, we just dilute this monopole gas so much that the visible part of the universe maybe not a single monopole left. So that's the way how inflation, for example, addresses this problem. So there is no conclusive remarks about that. Yes, some theories give that to us, but they are not something that we can directly measure, at least not right now. So that's as much as I'm familiar with that. I'm sure there are more things. People look for them, and there are very concrete analysis of that, but actually my research was never connecting to that. But I know a bit. Yeah, I can probably talk about that more if necessary, if somebody is interested.
Because I mean, it's interesting because I think that the LHC accelerator has energies that can, for example, detect or probably detect the direct monopole.
Yeah,
if it exists.
Yeah, there are bounds on that. Yeah, there are many bounds in different states that you believe they should be there, but they're not there. So they must be heavier than if they're not there. So, or maybe the interactions are so weak that you don't really produce them, even if they're light. So you can always find ways to say why you don't see them, but the fact is that we don't see them right now. Yeah. So whether it's, as I said, whether we just don't have them because the true theory does not contain them, or which I don't think it's the case. They may exist, but if they exist, then there is just no way we can actually detect them at the moment. Yes. There are different methods that are being developed. I'm not quite familiar with the exact experimental situation right now, but there are different methods that I heard about. Just a second, because my phone is about to shut down.
No battery.
Yes. No worries. I just turned on the button of this charger, so that should work. Yeah. So what I just mentioned is basic direction, research direction, particle physics. There are a few more related directions related to, for example, collective phenomena in quantum chromodynamics. We are talking about strongly coupled medium regime when then we have a medium and high density of multi-particle configurations with many hundreds of particles that are being produced in proton-proton collisions, and there are already some collective phenomena that cannot be predicted by ordinary quantum field theory, or at least not the one which is in textbooks. Then what is called temperature effects start to become important, and that's what thermal quantum field theory is being developed, and I have been working recently on that too. But there is, of course, first principle formulation, which has very complicated structures that may only be really calculated close to equilibrium, thermal equilibrium, but there is not a real consensus about the theory beyond the thermal equilibrium, and this language exists, but it's very hard to calculate anything, so that people come up with phenological models which seem to work, but they just play the role of parametrization of thermal effects, and usually they applied for describing multi-particle production processes at LHC when you hit complicated systems like heavy ions, and then lots of different phenomena appearing when you collide heavy ions that, for example, do not appear in electron-positron collisions. And those are effects of the medium that we try to understand also, and that's part of my research, is to model the heavy ion collisions, to model the medium-induced phenomena, is to model the multi-particle distributions inside the protons and inside the nucleus, and that's what I also was working on. That neatly connects to the big research topic nowadays, is to understand the structure of the proton, the structure of the nucleus, in a sense of distribution of the constituents. So if you take a proton, we know that it's made of 3 quarks swimming inside the gluonic cloud, and we would like to understand what is the distribution of the quarks inside and the distribution of the gluons inside at different kinematical domains. And that's a big part of the phenomenological QCD phenomenological research, is to understand the proton structure, understand the hadron structure in general, and also how objects made of quarks and gluons are forming in the real time, how they being, so to say, emergent from the scattering processes. And this is also quite fascinating topic that also connects to Emmanuel's research. By the way, Emmanuel's group is doing all that for many years, and we are collaborating very actively in that with a few students of Emmanuel and mine there at UFSC. So then, of course, there are many connections of this type of physics, particle physics, new physics, and also QCD, hot QCD dynamics, to cosmological environment, how QCD plays out in cosmology, like when it comes to the hadronization of the universe as a whole. Like when you come from the quark-gluon plasma phase, then this phase undergoes phase transition and turns into a hadron gas, which expands together with the universe. How that happens in real time is one of the biggest cosmological problems we are trying to understand as well, and I spent quite some time thinking about that recently. Then there are more similar type of dynamics, similar in the sense of phase transitions also happening around the higher energy scale, where the universe passes through the so-called electroweak phase transition, when electroweak symmetry gets broken by the scalar field condensates. And while we have the standard model that is usually formulated in a zero temperature limit, and all the collisions of particles and weak scale processes happening, and Higgs boson in particular interactions all happening at 0 temperature. In the universe you have huge temperature, and how these processes play out in the thermal medium, how this electroweak phase transition happens in reality. It's a big question. For the baryogenesis, for example, we need a first order phase transition. However, in the standard model, the phase transition only second order or smooth crossover, so it cannot be achieved in the standard model context. This is one of the motivation to add additional scalars and calculate the shape of the thermal effective potential and how it evolves when the universe cools down to lower temperatures. And looking for the characteristics of the phase transition is one of the hot topics nowadays, and I've been working on that as well. One way to probe the dynamics of primordial phase transitions at very high temperatures is by looking at the so-called gravitational wave signatures, because when you have the new phase, the bubble of a new phase that's been formed, it goes through the medium and it hits the medium and produces the gravitational waves. There are several mechanisms on that, and nowadays proposals for the measurements for the gravitational wave spectrometers, which have been discussed extensively in the literature. So we've been extracting the gravitational wave signatures that could be potentially measurable at future facilities. And basically this allows us to extract also the physics information from potential measurements of gravitational waves about the structure of particle physics there, in particular if there are additional contributions to the Higgs potential, additional particles, additional interactions. All of that we can in principle access through this gravitational portal. So that's another kind of chapter of my activity. And everything that relates to that, particular to the QCD dynamics at small and large space-time separations, electroweak dynamics, and beyond the standard model dynamics, all of that connects neatly to the structure of the ground state, so-called ground state of the universe, or the physical vacuum. So basically, ultimately, what we are doing is trying to understand that structure and how it evolves dynamically in real time. Yeah, so maybe I should go to another. Yeah. Well, actually, here I already kind of said many things. This is the slide about the structure of the standard model as we know it, and this is called cosmic DNA. And already Nobel Prize for that was given before. The only question about consistency, and right now we already spent, I don't know, almost 2 decades on verifying the structure, and there was not a single direct measurement that would disprove anything in this structure so far. There are a few deviations that are very interesting, like muon anomalous magnetic moment, slight deviation there. But still very consistent, apart from those issues that I mentioned that still motivate us to go beyond. And even the understanding the structure of the standard model itself as it comes out from some more fundamental interactions is the biggest question. Here, for example, the naturalness problem, which appears, for example, the mass of the Higgs boson is way smaller than the Planck scale, and of course, technically, we don't know why. Is there a desert, as people call it, desert between 100 GeV and 10 to the 19 GeV, which would be a huge desert? We don't know, and that's kind of the motivation for new physics. And here I just list a bunch of different problems or questions that we would like to address. I mean, they are all inspired by the measurements, but for example, the neutrino is 10 billion times lighter than the top quark, at least, maybe more. And this kind of properties, splitting between weak scale and the gravity scale by 32 orders of magnitude, you know, these are kind of the problems that are bothering our minds for ages, and no compelling solution so far found. Well, actually, there are proposals. We are proposing a so-called grand unified field theory that actually has a strong potential to predict the properties of the standard model as they come out from the measurements, like the mass spectra and the mixing parameters that are just, you know, parameterized but not really found from the first principles. So we're trying to build such principles. They, for the most part, involve dynamics of additional dimensions. You know, our space and time has only 4 dimensions. Well, only. That's what we used to have, at least for all measurements that we have. However, that might not be a fundamental constant. We may have additional dimensions at ultra high energies, and that's one of the proposals, is to look for much more unified theory that exists or lives in a higher number of dimensions, and then by some phase transition reduces down to the standard model. So that is one of the questions that we are also trying to understand. And that's basically the scheme for that theory. You can think of not being having a huge desert between the Planck scale and the electroweak scale, but that desert can be filled with many additional symmetries that can be larger than the standard model, and they contain the standard model symmetry, but they gradually get reduced by multi-step breakings all the way down to 100 GeV. So that, of course, the whole scheme is complicated, but it also very neatly unifies a lot of parameters and a lot of particles. For example, in this scheme, we can unify all the Yukawa interactions into just one coupling, and all the Higgs boson gets unified with the leptons, for example. There's a lot of neat features like that. And these are the basic problems that I already mentioned briefly. Is the transitions in the vacuum. We have the scale for the strong interactions, 1 GeV roughly to the power of 4. Then we have electroweak interactions that give you the scale 10 to the 8 gigaelectronvolts to the power of 4, and the gravitational interactions contribute with the scale 10 to the 76 GeV to the 4th. And that's basically the energy scale of the vacuum configurations that have been added to the physical vacuum. And the problem with the dark energy that I just briefly mentioned before is that all of this are much, much bigger than the scale of dark energy. So the dark energy scale here is away by something like 50 orders of magnitude from the strong interaction scale, and much, much more from others. So one has to eliminate these contributions to the vacuum somehow, and the mechanism is not quite clear. There are proposals there, and we also contributed to that at some point. So we have some idea of cancellations of these contributions at each respective energy scale. So in the QCD, there is this famous picture to the right. We have this coupling constant that has two different regimes: confined regime, where the coupling or the strength of the interactions between the quarks become very, very large. That's called confinement regime. That's basically when they are far away, far apart from each other, and they cannot live on their own. And they must be confined inside the bound states. So there's a strong field that binds them, which can be represented as a string. That's the gluonic field. However, if you try to stretch that field, that string breaks down into pieces, and those are what we know as hadrons. So you never actually produce the free quark or anti-quark. You always produce them in pairs, like QQ-bar pairs, and those are basically the mesons, like pions. So, and the static QCD potential between those having the characteristic linear behavior, which is the string potential. So we are kind of in the realm of strings here, but at the QCD scale. In the other regime, when the distances between quarks become very, very small, then the interactions practically switch off. That's why we are talking about asymptotic freedom there. And those three gentlemen, Gross, Wilczek, and Politzer, were getting Nobel Prize for actually calculating this behavior from the first principles of QCD, which is one of the major achievements there. Unfortunately, the problem is to understand the confined regime. So how that happens in real time, we don't know. We have some models, have some ideas, but there is no complete picture yet. So there is no way to simultaneously describe on the same grounds the dynamics of hadrons, which are bound states of quarks, and this partons, what we call quarks and gluons on the other side. So there's only a way to kind of limit the theory to one end or to another, but there's no universality here. So we cannot do that universally, and there are big problems with that. Yeah, so with the dark energy, we had this idea that the confinement of quarks may have an implication for dark energy, due to the fact that there are different fluctuations in the QCD vacuum that contributes to its energy density. But those contributions from this different type of fluctuations, we call them chromoelectric and chromomagnetic ones, they actually come with opposite sign. And under certain circumstances, these contributions to the vacuum energy or the ground state energy can just cancel each other. And that happens only macroscopically at large distances, larger than the Fermi scale. So, so dynamically, that could cause two effects. First is the confinement itself, simply that the color charge leaves only during the period of that fluctuation. But actually, when you look at the wavelengths of gluons or quarks, for example, which are far beyond the cancellation scale, then the field density just drops exponentially. So there's no any color field there, and that happens precisely because of this cancellation. So confinement can be explained due to this cancellation, and also simultaneously as a byproduct that explains why the dark energy is so small, because the QCD vacuum itself eliminates dynamically itself up to almost 50 orders of magnitude. There is a small effect on top of that 50 orders of magnitude, that is quantum gravitational effect. So there is a cancellation to zero order in quantum gravity fluctuations, but there's a first correction to this energy spectrum of this vacuum fluctuations that is not cancelled, but that is suppressed by the coupling of gravitational interactions, the Newtonian constant essentially, and compared to the zeroth order fluctuations that cancel out. But in the first order, they're not cancelling out, and that produces the observable cosmological constant. And that was our mechanism. That seems to be the only dynamical way to achieve that, at least from the QCD point of view. All right, that's probably it. I don't have to say more. I think I already said a lot. What do you think?
Oh, that was great. That was great. Roman, let me ask you just a few things, if you allow me.
Yeah.
This universal model, or the theory of everything, this unification theory.
Yeah.
What you showed here, it's a lot of different kind of energy scales and little bits of different theories to explain a little bit of this and that. Of course, you have this standard model, but as you said, it doesn't explain everything. It's great, but it doesn't explain everything. For us to be able to get a unified theory, we have to understand first dark matter and dark energy, or the normal matter is already so complicated, and the dark matter and then dark energy, they can be complicated as well, and we have to understand them to get a unified theory at the end, or doesn't matter?
Yeah, well, of course, unified theory has to possess all these features. Otherwise, it would not be a unified theory. It would not be a candidate for the true theory of nature, which works better than the standard model. So the only way to come up with a theory which works better than the standard model is the theory which addresses all these problems, or at least one of them, I would say, because standard model has this whole set of issues. I can go back to this slide where I had those issues listed, for example, here. So all this bunch of bullet points here somehow is an issue. It's not like an open issue where you make a, so to say, a measurement and you discover something that doesn't totally fit in the standard model. Surprisingly, the collider measurements all fit the standard model. There's no question about that. But there are still inconsistencies. There are still blind spots. I would say just a lack of information that standard model can't provide us, and one of such questions, of course, dark matter, but there are a number of other similar questions, and all these questions eventually need to be resolved by a better theory, which is more unified, more extended, maybe built on a new set of principles, and we don't know that. It's like trying different things. We try various extensions of the standard model using or not using the same principles as the standard model has been built upon. And standard model is really beautiful, if not unique in many senses. So any potential extension of it has to satisfy a whole bunch of constraints. Of course, it has to reproduce standard model with the accuracy that we have today's measurements, but also at the same time, it has to give us some ways to technologically verify it in a near future, because if it's not verifiable and if it's not better than the standard model, then we don't need such a theory. So it has to be better in certain ways, accommodate dark matter, have an explanation for dark energy, have a way to be verified somehow at collider measurements, at astrophysical measurements, gravitational wave measurements. It should somehow fit into cosmology much better, because standard model is not really doing that great. Of course, one problem is dark matter and dark energy, but another problem is baryogenesis, neutrino mass problem, and a few more. Inflation is, as far as I understand, is not really part of the standard model. I mean, you have to put a bunch of additional assumptions on top of it anyway. So there's so many questions that we would like true theory to address. So that's why we need to look wide. We cannot just look in one specific direction. Actually, many physicists do that. They just take neutrino problem and work on that problem for the whole lifetime, maybe not even asking themselves about other issues. This is not my approach. My approach is to look globally, because I know that good theory has to address all these issues, and I need to know everything about each. If I just know something about one, maybe it's not sufficient. Maybe I would eventually even solve that problem, but that would not be satisfactory anyway, because I can't address any other problem. So,
but when you are studying basically the vacuum structure, or the ground state of the vacuum structure, you are facing the issue of trying to solve all these problems.
I try to do what I can. Ordinary physicists may have huge ambitions for lifetime, but we also have to be realistic, right?
Yeah.
So there are a few things that can be considered separately, and QCD is one of those. We can try to solve QCD confinement problem independently from solving the Higgs problem, to some extent, I would say. Also, the dark matter, it has beautiful solutions in supersymmetry, apart from the problem is that supersymmetry has not been found. So there are many... It's
a beautiful theory.
Yeah, it's just beautiful theory, but it becomes ugly if you put constraints from LHC on it. It's still possible to fit it, but it's ugly. It's not the one that you would probably expect for the theory to be. So it has to be something else. And then is this all these kind of questions bother you? It's not like just one of the questions. It's just so many things that you have to be bothered about to actually come up with something wise. That's my approach.
Okay. Come on, I think it's a lot of things. It's good enough for us. What do you think?
Okay. Well, I guess I covered, at least I mentioned the things that I'm doing for lifetime. There are many things that I would still like to do, but I just don't have time.
No, that's nice. Professor Hoban, thank you again for your presentation. I think that you're participating on this series of videos. It's very important for our students and for actually everyone that's seeing this. It's a lot of very interesting topics, very interesting discussion in physics. There are people that say that everything important was already discovered in physics. Your presentation demonstrated the contrary of that, right? There is a lot of things that must be discovered in physics, which we're gonna give is actually a lot of work and jobs for the new physicists that we are forming here at the university.
Sure.
I believe that if everyone has any question, they can ask us, the coordination, or even you, send you an email, or even to the past graduation coordination that I believe that we can talk. And I know that you have many students and have many collaborations. Congratulations on that. I think that that's very important. And well, that I'm going to appreciate, and thank you again for participating. Thank you very much.
Thank you very much. See you.
See you after coronavirus.
Yeah, definitely.
Bye-bye.
Bye-bye. Bye.
Nice. I mean, I'm very not familiar with the field, right? But I guess I can maybe interact a little bit, maybe later.
Yeah, you can interact at any time. I just don't know if that has to be like in the form of a seminar or in the form of...
No, not really. Basically, the people that are gonna see this video are gonna be our undergrad students from the first year, and maybe people that are not our students, right? So the idea is to make a little bit of propaganda of the course, or the physics course in the university, to bring people to physics and make actually our undergrad students to do some scientific research.
Right.
So basically that's the goal.
Yeah.
So I mean, we should avoid any complicated language, right? And give, I mean, this flavor of how would be amazing to work with particle physics and high energy physics and quantum field theory. I mean, it's that exciting. I believe it is.
Yeah, Sweden, but I can say that I'm a visiting professor.
Collaborating with the Manuel group if you want.
Yeah, exactly.
Okay, so let's... Olá pessoal, tudo bem com vocês? Bem-vindo a mais uma série de... Start again, sorry, I just... The Portuguese went all wrong right now. So how is your Portuguese, by the way?
I know a bit, but I can't really speak fluently at all.
Roman, thank you again for your... Sorry, let's start again.